Hello, I'm Max Koo, Senior Developer at PolySwarm Technologies, and welcome to this introduction to Perigord, an open source Golang DApp development framework developed by PolySwarm. In this video, we will discuss some background information on Ethereum and Solidity development, give a quick overview of why we developed Perigord, walk through the use of the framework with a coding demonstration, then provide some closing thoughts. So what is Ethereum? Wikipedia defines Ethereum as an open-source, public, blockchain-based distributed computing platform featuring smart contract or scripting functionality. Similarly, Ethereum.org states that Ethereum is a decentralized platform that runs smart contracts, applications that run exactly as programmed, without any possibility of downtime, censorship, fraud, or third-party interference. Exactly as programmed is one of the key strengths and weaknesses of the Ethereum platform, as smart contracts have shown themselves to be useful in many new applications and domains, but remain susceptible to the same types of bugs and logic errors which plague other software platforms. Ethereum can be modeled as a state machine whose state can be modified by transactions, similar to other blockchain implementations. Ethereum's transition function between states, however, can include Turing-complete computation. Ethereum miners race to solve a proof of work to mine a new block of these transactions, choosing which transactions to include based on an incentive. A distributed consensus is formed on the result of these transactions by verifying this proof and the attached computations upon the mining of a new block by all nodes within the network. The code which drives these computations is contained in smart contracts, which power decentralized applications on top of the Ethereum platform. The actual code contained in smart contracts targets a virtual machine known as the EVM, or Ethereum Virtual Machine, which is a stack-based virtual machine with certain characteristics enabling easy implementation of cryptographic operations. Execution in the EVM is bounded by gas, which is a payment attached to a transaction, which pays for the computational resources used. If execution of a transaction runs out of gas, the computation is aborted, but the gas is not refunded. Consensus between Ethereum nodes is formed by verifying a proof of work attached to a block of transactions. That is, solving a cryptographic puzzle which is hard to solve but easy to verify, then verifying all the transactions in the block. All full nodes execute the EVM contract code for each transaction in the block as part of this verification process. Concerns about the scalability of this approach are fueling recent efforts to enable various scaling approaches such as sharding and off-chain payment channels. Now that we have some background about how Ethereum works, let's talk about some of the security issues which have arisen with smart contracts. Several high-profile attacks against smart contracts holding large amounts of ETH have occurred, such as exploits for the Parity multi-sig wallet bug and the DAO hack. Damages resulting from these bugs have been estimated to be around $30 million USD and $70 million USD, respectively, based on the value of ETH at the time. Both of these vulnerabilities resulted from high-level logic errors which can be traced to errors in the Solidity code for the contracts. EVM itself functioned as expected and executed these transactions exactly as programmed. This raises the question, how can we improve the security of our smart contracts besides manual audits intending to find all the bugs? Contracts need to be right all the time, whereas an attacker needs to be right only once, so this approach does not scale. Put differently, how can we improve the ecosystem to make it harder to get it wrong? Let's look at some of the pitfalls which can befall smart contract developers, beginning with a quick overview of Solidity. Solidity is the most popular high-level language for smart contract development. Its syntax and structure is based off JavaScript, meaning to provide a comfortable environment for web developers to get up to speed quickly writing smart contracts. However, its semantics are subtly different and in some cases easy to get wrong, which leads to vulnerabilities. This is not meant to be a complete Solidity tutorial, however we will go over the basic structure of Solidity smart contracts to give some background. Solidity files define either contracts or interfaces for transactions and offline calls to interact with, or libraries meant to be called from other contracts. Inheritance, similar to traditional object-oriented inheritance, is supported, as is multiple inheritance. Contract bodies can contain type definitions, state variables, functions, and event declarations. Typical primitive types are supported with a notable lack of floating point number support. Aggregate types can be composed from these primitive types, including structs, enums, and mappings, which are similar to dictionaries in other languages. Unlike JavaScript, Solidity is statically typed. Functions in Solidity can be designated as payable to receive ether, pure to indicate that they do not modify state, or can be decorated by user-supplied modifiers to check invariance. Multiple return values are supported. Special functions such as constructors and fallback functions, or the functions called by default on a contract, are defined by naming conventions which can cause issues during refactoring. Events are also supported which use EVM's logging facilities to enable triggering callbacks in front-end applications while processing transactions. Here is an example of a Solidity contract from the Ethereum website, which represents a token with the basic functionality of mapping Ethereum addresses to a balance and managing transfers between accounts. The constructor initializes the token supply assigned to the instantiator, and the transfer function allows creating and updating fields in the balance of mapping to enable transferring funds. Let's talk about some of the hard-to-spot errors which can arise when developing smart contracts in Solidity. Looking at the following snippet of a contract, can you spot the vulnerability? I will give you a few seconds to look it over. Feel free to pause the video if you would like more time. Okay, we can see here that a fallback function is declared for this contract. This means that if a transaction attempts to call a function in this contract which isn't matched, it will delegate this call to a library, passing along the data of the call as the new set of parameters, and executing the library call in the context of this contract. Unfortunately, this means that any public functions in the library can be called in the context of this contract, violating our assumption that the contract can only be initialized by its constructor. Here we could send a transaction which sets the owner of this contract to an account owned by us by calling the init wallet function after construction time, enabling us to drain all the ETH out of this contract. Because of the implicit behaviors of the fallback function and the relationship between libraries and contracts, this vulnerability can be hard to spot, but has disastrous consequences. As a note, this is a simplified version of the vulnerability which led to the parody multi-sig wallet hack. Let's do one more. Again, I will give you a few seconds to analyze this short snippet. In this example's withdrawal function, first an account's balance is checked, then the value is sent to the account, then on success the balance is updated. The vulnerability arises because the call to the recipient address can itself be a contract with a fallback function which recursively calls into the withdrawal function again, receiving the amount, but then redirecting execution before the balance is updated. This cycle can continue until all the ETH in the contract is withdrawn. Relationships between contracts caused assumptions about the execution flow of a transaction to be violated, which can be hard to spot due to the non-obvious relationships between contracts. This example is a simplified example of the DAO hack. In conclusion, smart contract development is young and the pitfalls are not all understood. Certain aspects of the Solidity language do make it easier to introduce bugs with large consequences in seemingly short, uninteresting snippets. Going forward, the lessons learned from traditional program analysis and verification, such as testing, static and dynamic analysis, and formal verification, will be increasingly applied to smart contract development due to the large stakes attached to getting it wrong. This will likely go hand in hand with improvements in the tooling and frameworks used in smart contract development. But what does the ecosystem look like today? Let's look at some of the tools currently used in developing smart contracts. The first would be implementations of Ethereum itself. There are several official implementations of the protocol, including ones in Go, C++, Python, and Java. The Go version is the most popular, however. This implements a full Ethereum node and offers an RPC interface, and can interface with either the main network, one of several public test networks, or form a private test network. In terms of developing smart contracts themselves, a very popular framework for smart contract development, testing, and deployment is the Truffle framework. This provides infrastructure for developing smart contracts and front-end interfaces in JavaScript, for creating automated tests in either JavaScript or Solidity, and for quick testing cycles using special features of the JavaScript test RPC implementation. Truffle's structure makes sense, as a common trend in smart contract development is a focus on developing web front-ends to smart contracts. However, this is not the only use case, and for many applications, native or back-end access to the Ethereum blockchain is desirable. In this environment, JavaScript frameworks are not typically the tool of choice, leading to a desire for better tools for native DApp development. This is why we've developed Perigord, which attempts to take a Truffle-style approach to DApp development, but is geared towards developing backend or native applications in Go. It provides a project scaffold and support library which removes some of the rougher edges surrounding interfacing with Go Ethereum, along with providing a consistent and therefore easier to understand structure to native DApp projects. Today, Perigord is young but functional and provides the basic setup for building, testing, and deploying smart contracts. In developing it, we have gotten very familiar with the Ethereum infrastructure and have endeavored to improve the process of using existing tools to develop native distributed applications. We hope that continued development and increased focus on native DApp development will help improve the ecosystem overall, along with increasing the utility of Ethereum in general. Let's go over a basic demo covering Perigord's use today. Alright, before starting, it is recommended that if you want to follow along with this tutorial, you be running a Linux system, have Perigord pre-installed according to the instructions at github.com/polyswarm/Perigord, and have Go Ethereum running a local test network setup. I have this running in this terminal window here. So to start, we will initialize a new project using Perigord init. This creates a project scaffolding under our Go root and creates some sample contracts for us. Let's examine what Perigord has generated for us. Here we can see that some sample contracts have been generated. Those are the Solidity files under the contract subdirectory, along with a good number of Go files. For the most part, these don't concern us except for main.go and the tests under the test subdirectory. Let's begin by looking at the contract that Perigord has generated for us. As you can see, this is an extremely simple contract that mostly exists just to show that your setup is working and that you can deploy a contract to your test network. We can build these bindings with Perigord build. As you can see, we have some warnings, but our contracts have been compiled successfully. We can confirm this by listing the ABI and EVM bytecode files generated under the build directory, along with the bindings generated under the bindings directory. The files in the bindings directory represent Golang bindings to our Ethereum smart contract. This is the main way that we will interface with our contract from our native code. Examining these files, although they're auto-generated, can be a good way to learn about the interface and what exactly is going on under the hood. So let's look at foo.go, for instance. As you can see, this is a lot of generated code. Most of it doesn't concern us, but we have the deployment function here, which we will use to deploy our contract to the chain. As well as our bindings for the function we defined. So this will call that bar function as defined in foo.sol. All right, so before we deploy this, we need to make one quick change to our configuration and point our key store value for our dev network to our local key store, which mine is located here. We can now deploy this contract to our local test network. This will take a few seconds as it processes the transactions that we are posting to our dev network. It's usually around 15 seconds per transaction. All right, our transactions have completed successfully. We can now, for instance, view the output from our Go Ethereum node and see that our contract creation calls have been completed successfully. So we've deployed our first contract to the blockchain. All right, now as far as interacting with this contract, we can do that both through our main application code defined in main.go and whatever other packages the developer wishes to provide. However, we can also test these contracts through a unit testing framework, which is done under tests created in the test subdirectory. One already exists for us for this contract, so let's go ahead and view it. For the most part, this contains the upper half of this file, this boilerplate that sets up our testing framework, which ties into Perigord's libraries. Our user tests exist down here. These mostly consist of getting a handle to our session, asserting that it was deployed correctly, then calling our function, and asserting that the return value equals what we expect. So if we run Perigord test, we expect this test to succeed. Let's try that now. This will redeploy our contracts. I won't make you sit through this again. I will pause the recording and come back once it's completed. All right, welcome back. We can see that our test has completed successfully, which is great. However, this is a fairly simple contract, so let's add a more complex contract to show off some of the features of Perigord and how to add in a migration and a new unit test. So for this example, let's grab the sample token ERC20 contract from ethereum.org/token. A link will be provided. And place that into our project. And we won't go too much into the functionality of this contract. If you wish to examine it more closely, feel free to check out the website. Again, that's ethereum.org/token. However, just know that this essentially is an expanded version of the sample token contract we showed earlier in the video and allows transferring tokens between Ethereum addresses. All right, so our contract has been added to the contracts directory. We can now build our bindings and our Solidity with Perigord build. And again, that completes successfully as expected. If we list our build directory, we can see new ABI and bin files have been created, as well as new bindings in the bindings directory. All right, however, we've created this new contract. However, Perigord doesn't know how to deploy it yet to the blockchain. So for that, we're going to add a migration. We can do this with Perigord add. All right, this has created a migration from the boilerplate in the Perigord templates into our migrations folder. So let's see what's been generated for us. All right, a lot of this is boilerplate. It does a lot, but it essentially sets up the account we wish to deploy from and then calls the deploy function that was created for us in our bindings. Again, we can view that by examining the generated bindings. And we can see here that this deploy function is what it's called. Typically, we don't need to modify much with the migrations. However, if our constructor takes additional arguments, such as this one, we need to provide those. So we can see here that the deploy token ERC20 function expects an additional initial supply in the form of a big int, a token name, and a token symbol, both of which are strings. So let's go ahead and add those parameters to our call to deploy token ERC20 here on line 24 in order to successfully complete this migration. So to do so, we'll need to import the math/big package to enable us to create a big int. We'll do that here in the imports. And then down on line 25 now, we will add in our additional parameters. So those are a new big int, and we'll just create a bunch of tokens. A string representing the token name, we'll just call this token. And a symbol, which we'll just call TKN. Now, if all has been successfully completed, we should be able to deploy this new contract to the chain. So we can do that again with Perigord deploy. And again, I will pause the recording until this completes. All right, welcome back again. We can see that our migration is completed successfully as expected. So great. So the last thing that we want to accomplish today is to show off how to create a unit test for this new contract. So to do so, I will again use Perigord add, this time with a test. And this creates a new test Golang file under our test directory. So let's examine this generated file. We can see here that it's very bare bones, but essentially creates all the boilerplate that we need to set up our test suite. And then our user tests go under line 27. So to begin with, I will copy the tests from our foo.go test in order to simplify the creation. All right, so essentially what this does, again, is grabs a handle to the session, asserts that it's created correctly, asserts that it's the right type, and then calls a function and checks the return value. So to modify this to work with our token, we'll change a few parameters. So here we're dealing with a token ERC20 suite. We're testing our token. Our session name is called token ERC20. Our type is token ERC20 session. Call this a token session just to keep things consistent. And for a simple example, we'll test the symbol function, which is a pure function on the token. So I believe that function name is just symbol, but we will check the bindings to be sure. And indeed it is. So here we expect to receive a string back, and that string should be our symbol, which, as you recall, is TKN. Let's confirm that quickly. And indeed, it is. And we don't need to convert this to an N64. All right, so that's the basis for the basic setup for our test. We should be able to run Perigord test now and receive a test pass. So once again, I will return shortly. Oh, we have a couple build errors to fix up real quick. Yeah, so let's try that again. All right, and I will return shortly. All right, and our tests have passed. So that about wraps up this quick Perigord tutorial. If you'd like to know more, please check out our GitHub. Pull requests are most definitely welcome, as well as our introductory blog post with a more in-depth tutorial. Let's wrap things up now with some conclusions. So, we've talked a bit about why we wrote Perigord and the niche it fills in the Ethereum ecosystem. But let's talk for a second about how and why we use Perigord at PolySwarm. PolySwarm is a decentralized antivirus platform powered by Ethereum, using economic incentives and the unique functionality of Ethereum's blockchain to promote innovation in the malware analysis space and timely and accurate intelligence regarding security threats. We use smart contracts and the decentralized nature of the blockchain to reward security experts from around the world based on results. We hope to lower the barrier to entry into the antivirus market and realign the economic incentives in InfoSec to favor finding malware over making it. Our goal is to enable security experts to write or adapt specialized microengines to interface with our threat intelligence marketplace, enabling specific, targeted state-of-the-art analyses to be applied to submitted artifacts with minimal developer overhead in getting set up. This means that a native DApp backend which handles communication with the Ethereum blockchain is perfect, as we aim to provide a convenient machine interface for developers and security experts rather than a front-end facing web application. The difficulties experienced in creating this backend using only the Go Ethereum bindings inspired the creation of Perigord, and we hope that its creation will improve the ecosystem as a whole and lead to new, innovative applications of Ethereum's blockchain. Thanks for watching. If you would like to know more about Perigord or PolySwarm, please connect with us on Twitter or focus on GitHub. Thank you.